for coming to the ACEAS seminar for this month. Before I start, I would like to just acknowledge the Ngunnawal people as the traditional custodians of the lands we're meeting on here at ANU today. I would like to also extend my acknowledgement to all countries participating in today's seminar and pay my respects to elders past and present. So today we're going to be hearing from Dr. William Scott. Will arrived here at ANU at RSCS just over a month ago. He is currently an ACEAS postdoc working with Roger Davies, where he's working on developing a glacial isostatic adjustment model using Firedrake, which is a finite element framework. Before Will arrived, he was completing his PhD at Imperial College London, where he was at the Earth Science Department under Professor Matt Pigott. And he also completed his undergrad at Imperial, and while he was there, spent time at UC Berkeley and at the Woods Hole Oceanographic Institution as a researcher. So Will's thesis was completed on using Firedrake to model ice-ocean interactions, which will be the topic of his talk today. Thanks, Will.
Well, thanks very much, Beck, and thanks very much for coming to my talk. So, yeah, I'm Will, and I'm going to be talking a bit about what I'm doing during my PhD at Imperial. And these are, I'd like to thank, these are my supervisors, Matt Pigott and Martin Seeger and Stefan Kramer at Imperial, and at BAS, Keith Nichols and Paul Holland. And then I've also worked a little bit with Ben Yeager and Dorothy Vallon. And so the structure of the talk is mostly about model development. So I'll sort of try and take you through the steps we've done to sort of verify the model and sort of different challenges we've had along the way, and then show a little bit at the end to do with basal crevasses and trying to apply this model to an interesting problem in ice shelf ocean research. And I recently had my first paper accepted a few months ago, so some of this stuff is in there. So if you'd like to have a look, it'd be nice to have a check about that. So I thought I'd start with this figure, because when I started my PhD, I thought it was great because there's loads of interesting processes going on and lots of interesting feedbacks. And I thought, oh, I could study all of them. But in the end, that's not quite how it works. But what the key thing for this research is that in Antarctica, we're interested in sort of the uncertainties related to the loss of ice from the poles and how that might contribute to sea level change. And particularly for the motivation for my PhD, people were interested in West Antarctica and the rapidly retreating glaciers that you get there. And what this figure is showing is looking at ice shelves. So you've got the glacier inland, which when it flows to form the ocean, if the geometry is right, then you can form these very long tongues of floating ice. And really what this figure doesn't really show is that they're always constrained, or generally constrained, by bays and valleys. So there's a lot of friction on the side. So this buttressing effect is slowing down how fast the glacier is flowing into the ocean. And if you get changes in the shape of the ice shelf cavity, it can have quite a big effect on how fast the ice is flowing into the ocean. And effectively, as soon as ice has gone past the grounding line, so that's this location where the ice starts to float, effectively from isostatic equilibrium, that's already lost into the ocean. So the sea level contributions happen. So what this is about is trying to understand about how the ocean affects the ice shelf shape through basal melting, and it's sort of being found as like one of the biggest drivers at the moment of West Antarctic glacier retreat. And I wanted to quickly talk you through one feedback that's kind of important for understanding some of these simple models, and that's called the ice pump. And the key idea is that the freezing point of ice depends on pressure. So as you go down to deeper depths, you're squeezing the ice, and the freezing point goes down. So it means you can get more melting at deeper waters for a given temperature. And when you have melting, that's an injection of fresh water. So fresh water is less dense than salty ocean water. So you have a buoyant-driven circulation. And then sort of in this simple picture, you've got this overturning where you get fresh water at the bottom going up towards the surface. And because the freezing point depends on depth, if you get to shallow enough depths, you can have refreezing. So it's either through fragile ice or sort of accretion onto the ice base. So there are these sort of weird and kind of crazy things, a bit like snow going upwards. So I'll show you some simulations of that towards the end. And it's sort of worth mentioning there are these runaway feedback mechanisms related to the geometry of the system. So everything in glacier dynamics is about balances. So basically how much snowfall you get versus how much ice is being lost through carving or through the ice shelf. And if those come out of balance, then you're going to change the shape of the glacier. And really, because of the geometry in West Antarctica, you have these sloping beds that are going inland, and people are interested in trying to understand how fast these, if you start to get retreat, how does that feedback on it? So here, this picture is just showing some ice flow modeling results, and the point I was trying to make is that there's lots of people have been modeling these ice flows, and they're finding that the glacier responses are very sensitive to how much melting you apply at the ground zone. So this particular study was varying whether or not you put melting on parts of the ice that have just started to float. And you can see that from the looking at the trajectory of the top panel and the bottom panel, there's quite a significant difference in the amount of ice retreat if you make small changes to your melt parameter. So that's what that was trying to say. So grounding zones are important, and trying to actually observe these regions is really complicated. So hopefully that's quite obvious that this is a theme from the ITQC project. So there was an international collaboration to look at Thwaites Glacier, which is one of the biggest glaciers of West Antarctica and changing very rapidly at the moment. And what they were interested in was trying to do direct sort of measurements of the water underneath the ice shelves. So this is right near the grounding zone. And so drilling through sort of hundreds of meters of ice using a hot water drill. So they have a big diesel generator and they melt ice on the surface and get these paddling pools of hot water, and then use that to drill through the ice and drop instruments down. And they've just had some nice results published this year. But the point is, it's very difficult to make these observations. So there's not very many of them. And then if you look at satellite sort of measurements for how the ice has changed in these grounding zone regions, you have this is looking at interferograms. And the point is, you have these very complicated geometries coming from the bedrock and how the ice is flowing. And so you can have these sort of pockets of water opening up. And really the point is, in sort of traditional ocean models for trying to model these things, it's very difficult to capture this kind of resolution. So kind of some of the motivation for this was looking at these pictures and thinking, how might we model these processes? And then there's also a sort of a side part that kind of I'll talk a bit more about later, but there's quite a big uncertainty in how to apply sort of the physics associated with melting in ocean models. So that really at the moment there's a lot of people trying to do different types of modeling to try and get to the heart of this. But it means in the sort of the slightly larger scale modeling, which I'm sort of on the edge of, you have to be very careful about your vertical resolution and your discretization choice. And I'll talk more about that later. And then sorry, I like this. There's one. I think this is going towards the end of the motivation, but I like this figure because this is from 2014, and this is using a submarine, like a little robot submarine that went under the ice, and it's got a sonar attached looking upwards. So this animation is looking at the base of the ice under the ice shelves. So you get these quite amazing features like terraces, so these steps in ice topography, and also big crevasses. So the ice base is kind of far from flat, but in a sort of a traditional model, all of that would just be sort of lost in like a grid cell or two. So there's quite a lot of unknowns about how does that change the turbulence, how does that change the amount of mixing, and they were the kinds of things that motivated this research.
What is the lower one? What is the upper one?
So this one is the elevation, and this is the slope. So it's just trying to give you an idea of because it's difficult to represent these things in 3D. So I think the point they were trying to make was this was all equal order aspect ratios. So this is kind of what it would look like. Right, so all of those complicated sort of geometries that kind of motivates maybe even finite elements. So and the key point is that you can use these unstructured meshes, which are good at fitting complicated geometries, and you can put mesh resolution where you need them. And there was at Imperial in the Earth Science department, there's a code called Fluidity, and they've used it for lots of different computational fluid dynamics and geophysical fluid dynamics applications. And the references here were specifically about ice shelves. So there was a few people over the years that would be using Fluidity to model ocean flow under ice shelves. And kind of the key things that they were doing was sort of keeping the full physics, so keeping the non-hydrostatic accelerations, so that if you go down to small meshes, for instance, modeling this crevasse, you still have physics that is approximating that system. And they're also using discontinuous Galerkin finite elements. So these are fine elements where you're allowing jumps in between the cells, and it's good for advection. So these are cutting edge numerical methods. And then so when I started, the group was transitioning over to use a new framework called Firedrake. And sort of the key summary is that this abstraction is useful. So what they do is that you can imagine in the developing these geophysical fluid dynamics or lots of different codes, there's lots of different people all interested in slightly different bits. And the key point about Firedrake is they split bits into different compartments. You have people like software engineers working on the software and trying to make things run quickly. You have mathematicians that can come up with good discretizations and stuff like that. And then you have people a bit more like me who are interested in the isolation physics, and we want to sort of set something up to run. And I've sort of got a list now of there's a few things that are sort of dotted across the world. Most of them have sort of started from Imperial, but so Thetis is a coastal ocean model. Gusto, there's an interesting sort of story about Gusto in that that's for the maths department at Imperial, and the Met Office in the UK, so the people that predict the weather, they're just changing over to using a finite element grid, and these people are testing out those discretization schemes for the Met Office. So if all the weather forecasts go wrong in the next few years, you know where it went wrong. But I'm sure they're doing a good job. And Spiro is a seismic full wave inversion code based out of Brazil, and IcePack is a very nice glacier flow modeling code out of Seattle in Washington for Dan Shapiro, and it's got some really nice documentation. So if you're interested in doing glacier flow modeling, that might be worth having a look. And then last but not least, Geodots. So that's based here with Rodri, and that's for simulating mantle dynamics. And I'm kind of fitting into this group to look at GIS. So I won't talk too much about that now, but we're interested in basically using Firedrake for these same things. And the key point that I wanted to make is that because in Firedrake you separate the maths from the sort of the software implementation, you have this level above the software that's really just symbolic maths, and it makes calculating an adjoint model, which I'll talk a little bit about later, but really just calculating gradients. It means you can do that in a much more efficient way than sort of traditional automatic differentiation techniques. So this is just a summary of what we're solving. So it's non-hydrostatic, as I mentioned. So basically taking the velocity from fluidity, and yeah, just doing boost exponential approximations and using DG finite elements. So they're the sort of the key things. And the key thing is that our sort of the math that we write down for discretization doesn't really depend on the grid. So we can do a whole range of different grid options, and I'll try and show a few of them during my talk. And what I try to sort of say is that just to sort of skip to here is just to show that the Python code really looks like the maths. So you can write down what the weak forms are for the finite element, and then you can write it down in Python, and it really looks very simple. So there's definitely a lot of advantages for keeping sort of like everything in the right place for this software implementation. And you can go and have a look at the code on GitHub. Right, so that was all sort of fluid. It's a fairly standard sort of computational fluid dynamics solver. But the thing that's making it interesting for this application is applying some boundary conditions, and I'll try and just quickly talk through it. So the key idea is you've got three equations for the conservation of heat, salt, and a linearized sort of freezing point equation, and you've got three unknowns. So that's the temperature and the salinity at the ice ocean boundary and the melt rate. So you basically just got a system that you can solve for, and it turns out you can just solve a quadratic equation by doing some substitution. And what we're sort of assuming here is that you have a computational domain where you're solving for the flow and the temperature and the salinity, but then we've offset the boundary, so the real sort of ice ocean interface is a bit off. And what that means is you end up applying these Robin boundary conditions where the sort of the gradients in the temperature and the salinity, they depend on the temperature and the salinity at the edge of your model. So that's how everything gets forced. And what the key, this will come up later, but this gamma T and gamma S, these are parameters that are trying to model the turbulent exchange of heat and salt across this boundary layer. And there's quite a lot in the literature at the moment. There's quite a lot of different ways of accounting for them. And kind of what the later part of the talk is sort of trying to understand about how careful you need to be with resolution. And I think that's still not really a solved problem. So, right, so I've given some motivation. So I just want to start sort of in chronological order, sort of showing where we started. And the key thing was we found very quickly it made it a lot more sense to compare with another model. So I was using MIT GCM to try and run very similar, basically the same simulations with the same mixing, the same grid resolution, all those things to make sure that we're getting similar results. And if you're an ocean modeler, you probably think this looks really small. So this is only a 10-kilometer domain near the grounding zone. And yeah, and there's sort of constant viscosity and diffusivity and slightly different vertical and horizontal. And then there's a restoring region on the right, which gives some slightly interesting dynamics, but you'll see that in a second. And on the top is applying these melt boundary conditions that gives you the flow. So I'll try and talk you through these different figures. So if you start on the top left, this is the horizontal velocity. And yeah, it's that flow. So red is flow to the right and blue is flow to the left. So really and Firedrake is on the top and MIT GCM is on the bottom. And really the point is they're showing this ice in the 2D, this very simple sort of overturning circulation coming from the ice pump mechanism, where you have the fresh water, where most melting at initially at the grounding zone, that's fresh water, and it's buoyant and it's rising up and overturning, and you get this overturning circulation. And kind of the nice thing is, broadly qualitatively, they're very similar, especially in the early spin up. And then what we were finding was on this right-hand side boundary, there was slightly like a sponge region where you're trying to relax it back to some conditions. And it was sort of, you can see there's some overturning, undulating density contours, which you'll see in a second. And Firedrake was doing a much better job at sort of robustly resolving that solution. And I'll kind of just quickly skip through. So this is the temperature. So again, you're seeing it's cold at the top. And basically this is this boundary layer forming and the flow going to the right. And if I just skip a little bit to later times, you can see that there's these undulations in MIT that are matching the grid scale. And really the culprit is if you look at the vertical velocity. So Firedrake is on the top looking at the vertical velocity, and MIT's got this grid artifact where you have these stripes coinciding with the grid. And it's not too surprising because effectively for our discretization, we're using DG with a linear slope, and MIT was using a constant finite volume. So we're basically at a degree order accuracy compared to MIT. So we always expect to be a bit slower, but for a given resolution, we expect to be about twice as accurate. So that's kind of what that story is telling. And then this is the melt rate. So first is, so orange is Firedrake and blue is MIT, and we were very happy that they basically look the same. And the reason you get these stripes is sort of an inherent thing to Z-layer models. So it'll be more obvious later when I've got a picture in 3D of the MIT GCM mesh. But MIT has these, to resolve a sloping interface, it has a fixed vertical grid resolution. So you're basically discretizing the domain as a series of steps. And you can get around this by changing what the top grid cell thickness is, by sort of introducing a partial cell technique. But what that's doing is changing how quick temperature and salinity can diffuse through that top layer. So you basically end up getting these stripes corresponding to varying melt rates based on the grid resolution. And in Firedrake, so that we could match the MIT GCM mesh, we were introducing sort of smaller triangles, so basically to get the same temperature. And we get basically similar. Oh, and then this is just to show in 2.5D, so you can add like an approximation of Coriolis. If you assume into the page direction is periodic, then you just have an extra scalar advection diffusion equation for the velocity component. And again, some of the dynamics settles down because everything's quieter, but basically the two models are looking very similar. So we were quite pleased in 2D. So basically that was in 2D in this very sort of simple setup. We were very pleased that things were looking the same. And then this was also, right, so then I just sort of wanted to talk about this 2B as some adjoint stuff that I was doing, which was kind of one of the motivations for using Firedrake. And the key, so if you haven't heard about adjoints before, the key thing is it's sort of a method for calculating gradient information efficiently. And what you can imagine the whole idea is you have this sort of objective function, also a number that's telling you, for instance, maybe how fast the flow is going through the Drake passage. And then you can calculate what the gradient is with respect to all the different grid variables. So for an ocean model where you have lots of unknowns based on a grid, you're going to have loads of unknowns that it means that if you were trying to sort of work out what these sensitivities were by just doing lots of perturbations, you wouldn't get anywhere. But what this technique does is allow you to calculate sensitivities independent of the number of those grid cells by solving another set of equations. And yeah, so the key thing is it can tell you about some physics. And normally what happens is it just tells you about the same thing, but in a slightly different way. So it's a good way of sort of trying to understand something in a slightly different way. And then the other thing is you can use it as part of a simulation. So you can imagine that if you change that objective function to an error, like a measure of the error between some observations and your model output, then you can start to try and reduce that error by tweaking what the initial conditions were, or maybe what your unknown parameters. So that's kind of the motivation. And it's quite common in quite a lot of fields, and in particular in atmospheric and also glaciological models, and in sort of wider ocean modeling. And this picture is from the ECHO project. So they're using adjoints to do their data assimilation. And I'm sure you've seen this very nice visualization. And so when I started the PhD, the sort of the people that had done this was back in 2012 using MIT GCM. And sort of since then, a few people have resurrected that MIT GSM adjoint ice shelf stuff. But really, there is kind of a fundamental difference between what MIT GSM and we do, because they have this Fortran code where you just apply automatic differentiation on every line of code. Whereas here, we've got this representation of the maths, which is a level above. So it means that you can avoid some of the pitfalls of having to go in and manually sort of make sure that the Fortran way of things doesn't go wrong. And you also have this discrete adjoint, which is sort of consistent with your forward equation. So that can be quite useful for when you're trying to do the assimilation. So anyway, so this is the same domain, and the functional is looking at the total basal melt rate at the final time step. So it's just integrating the melt rate. So just trying to get it and seeing how they're sensitive to the temperature and salinity fields that evolve in time. And the key thing about adjoints is that adjoints, so when you've got real numbers or real matrices, adjoints just means taking the transpose. So you can kind of, from this schematic, kind of see very hand-wavily that if you have like an advection from left to right, you'd end up starting at U0, and then U1 depends on U0, U2 depends on U1 and U0. So you have this lower triangular matrix structure. And because that's all a linear system, the adjoint is effectively just taking the transpose of that. So you end up with a upper triangular matrix where your sort of initial condition for U0 has turned into like a final condition on lambda2. So you sort of start by solving the sensitivity with respect to lambda2, and it starts to propagate backwards. So in a time-dependent model, what happens is that your adjoint sensitivities are flying backwards. And that will be hopefully obviously in this picture. So what this is showing is these sensitivity fields of the sort of the total basal melt rate to the temperature and the salinity. And if I just sort of stop it at the beginning, so this is looking at the final time, because that's when we're evaluating this objective functional. And the key thing, so you're looking at what the sensitivity is at the final time. And if I sort of play it, you can see how, so red means that you have, if you increase the field at that point, then the total melt rate will go up a bit. And if you decrease the field, then it will go down, and it's vice versa, the blue.
What is your objective here? Is it like the amount of melts you get?
Yeah, so it's just integrating this melt rate along the ice shelf. So it's just trying to sort of see how that's sensitive to the temperature and the salinity. And what's kind of interesting, and it's basically you have this high patches of sensitivity that rotate anti-clockwise, and it's basically you're just looking at this ice pump mechanism in reverse. So where in the forward model we had this clockwise circulation with the flow going up the ice shelf, now the adjoint is taking things backwards. And what you see if you go to far enough times, then you sort of lose sensitivity to the initial conditions. And sort of the other interesting thing is that the signs of the two fields are the opposite way around. So if you think about thermodynamics, you might think that they would be the same, because if you increase the temperature, you'd expect the melt rate to go up. But if you increase the salinity, then you'd expect the freezing point to go down. So you'd also expect the melt rate to go up. But actually, it's probably looking at because these temperature and salinity fields are very coupled in terms of the buoyancy. If you scale the two sensitivity fields by the sort of coefficients in the equation of state, you basically end up getting the same patterns. So basically, it's sort of showing that probably buoyancy coming from the salinity is sort of the main cause of this melting, and you're getting faster flow from the voids. So yeah, so that was kind of some very preliminary stuff, and but I wanted to move on to look at sort of more towards to 3D test cases, and what motivated this is, so before my PhD there was this test case called Isolate Plus, and the idea is that people would try and run these simulations of an idealized 3D cavity to sort of compare the results, and I think that was a few years ago now, and there hasn't really been there's been a few papers trying to sort of get to the bottom of it, but they haven't really done a big comparison yet. So I think it was a bit more difficult than I thought. And so the point is that's that. So we were trying to go from a 2D to 3D, and there was a bit of a story involved in us having to change our discretization strategy to be able to do these large domains. And most of that was revolved going from having sort of tetrahedral meshes, so that were stretched, to looking more structured. So by having an unstructured in the horizontal, but keeping a structured discretization in the vertical. And Firedrake has this nice interface for doing this, and it's kind of one of the selling points for Firedrake compared to other similar frameworks like Phoenix or Deal, in that they have this sort of representation where you can split the vertical and the horizontal part. So if you are starting to do more geophysical fluid dynamic simulations, this is a good strategy. And this was a slide just to sort of show that you have to be a bit careful about the types of finite element choices you make. So when you have this velocity and pressure system with an incompressible flow, you've got a saddle point system. So you just have to be careful that you don't choose a velocity and a pressure element pair that leads to spurious grid lines. So here is just showing the pressure fields for a bad element pair that gives you some checkerboards, and for a good element pair that doesn't. And so I'll just sort of skip through these very quickly, but these are basically similar things in 2D, just to show that in our sort of new strategy against MIT and Firedrake, we're still basically doing a very good job, especially once the things have spun up a bit. So that was the velocity, and then a similar thing for temperature. And again, you're sort of seeing these sort of plumes bursting out, but basically because the initial conditions weren't in balance with the melting. So you're sort of applying this immediate melting, which then changes the stratification a bit and changes the velocity. But after about 100 days, most things have quieted down and you get back to a steady state. And then this is to show the melt rates, and just to show that, again, we were very similar to MIT in 2D, and that you still have these sort of striking problems with the grids based on this step representation of the topography. So what you can do is you can change the grid for Firedrake, and this is a representation with these extruded meshes. So on the top one, you have a constant fixed vertical resolution, whereas on the bottom, you have a fixed number of layers. So it's like a terrain following mesh. And so the key thing is you can, so the mesh resolution is getting finer at the grounding line. And if you sort of look at the thing about the sigma stuff, is that you get a much smoother representation of the melt rate, because the change in the grid size is only happening very slowly over the ice shelf. So you lose so there's some interesting dynamics coming from that ice step. But basically you have this smooth approximation of the melt at earlier times, compared with the Z, which has these big stripes. But broadly here, and this kind of shows that these are sort of a bunch of different sort of results with MIT, and it's the big yellow one. And the Firedrake ones are the reds and the blues and the blacks. And what that's just showing is that really for 2D, all the results were quite similar. So there wasn't too much difference in the melt rates. And I sort of had in bold that you have to be a bit careful about limiters. So with these DG finite elements, you want to make sure that you're conserving. You don't want to have overshoots and undershoots in your temperature solutions, especially if you end up getting things like negative salinity, because then things start to go bad. So this is sort of just showing that you have to be a little bit careful, because the traces can influence the limiters can influence what your melt rate is for this case. But it sort of turns out in 3D there's a more minor effect. So this is sort of where I was trying to get to. So this is this sort of 3D simulation, and on the left you've got the MIT representation of this cavity. So you've got this sort of grounding zone, and an ice base that's sort of got some like a valley shape, And so someone told me at one point it looked like a penguin jumping into an ice block, and I could never really unsee them. So if you think so too. And then on the right is the Firedrake mesh. So we've got this unstructured representation in the horizontal, and then a structured representation in the vertical. And based on the 2D stuff, we wanted to keep going with the sigma layer, the terrain following mesh, because it seemed to give better, like smoother melt rates. So at that time, this is the best thing to do. And I've had that. I didn't explain that schematic before, but that's just showing what the horizontal velocity element looks like. So it was sort of inheriting some of those DG properties by being discontinuous in the normal direction, but continuous in the horizontal, in the tangential direction. So you can have these sort of slightly funky finite elements, and Firedrake can deal with that for you. So this slide was kind of was then where in 2D everything had been working quite well, and that you could run these simulations, and MIT and Firedrake would look very similar. But if you look on the left, these are the melt rates sort of averaged over the grounding zone region. So you generally have higher melting at the grounding zone because it's deeper. So you've got this freezing point going down, and you've also got a warmer water at the ice base in this particular test case. Sorry, water warmer at depth in this test case. And what the blue symbols are showing is that the melt rate for MIT at different grid resolutions. And really, you can see that there's no sign of convergence. So the sort of the isometric protocol was to say everyone should have about 20 meters of vertical resolution, or sort of 36 layers. So because there's this sort of difference between having Z and sigma layer models. And what you can see is that this, if you start to refine the grids, your melt rate just keeps going down and down and down. And it's less obvious, but if you look at the red line, so this is the Firedrake results, and we also see the same effects. So you have this, so the red line here at the top, and then the gap to here, to here, and to here is basically not showing sign of convergence. Well, that wasn't so good. So we were trying to work out what's going on. And if you look at the sort of the plan view of the melt rates, you can see that qualitatively MIT at the top, at this sort of coarse resolution, has higher melt rates, which these sort of stripes end up with sort of spurious things coming from the steps that are moving through the domain. And if you refine the grid, then you can see that these effects disappear. And qualitatively, you look closer to Firedrake. And what this was sort of so this has been shown before in a paper by David Gwither, who's in Australia. And so the key, what they were showing was that if you have the ROMS, which is a sigma sort of terrain following model, so a bit like Firedrake in this configuration, and COCO and NPAS that are more like MIT and having a fixed vertical resolution. The key the key thing in this protocol was that if you remember, there was that gamma T that was part of the melt parameterization. This was an unknown that they were using to tune the models. So the key idea was that you would sort of run the simulation for a bunch of different gamma T variables, and then see how and then try and get to a sort of a tuning melt rate of 30 meters per year. But what they were sort of showing in this figure was that ROMs with the terrain following model and a finer vertical resolution just couldn't even match this 30 meters per year. That was sort of their maximum melt rate they could achieve. And sort of they looked at it in terms of how do you vary this gamma T to try and change the melt rate. So I just wanted to quickly show some cross sections through the model. And so this is looking at the temperature and the velocity for the coarsest MIT, the finest MIT, and our model. And at this particular location at the grounding zone, you've got about sort of 100 meters. About 100 meters of ice thickness. So for the 30 layers, that ends up the DZ, or the sort of the vertical resolution of 2.5 meters ends up being about 30 vertical layers inside the cavity. So, and sort of qualitatively, you can see how some of the stripes in MIT and the velocity start to disappear, and they broadly do look quite similar if you squint your eyes, but they're not that. And what's going on is that really when there's sort of these two competing effects when you have melting. So in the very in large slopes, you have this sort of simple idea that we had before with the ice pump, with the overturning flow, and you've got this buoyancy-driven circulation leading to sort of a plume-like behavior. But when you start to have much shallower slopes, which is what's probably more representative of real ice shelves in this test case, is that melting is causing stratification. So you've got this stable stratification coming from freshening, which means that you've got fresh on top of salty water. So that if you had a flat domain, you have this stable configuration. And what that's doing is it's insulating the warmer water below from the ice bed, because you've also got colder water at the surface. So the salinity is controlling the density, but you've got this temperature, warmer temperature below that's being insulated by melting. And then this is kind of what this, and what's happening with, so what's happening with, this is now just looking at Firedrake runs, but looking at 3 different resolutions, vertical resolutions. And if you look sort of zoomed out at a depth profile of temperature with depth, you can see that basically all the models are doing very similar things. And that you have, at the base, you have this depth profile, this sort of linear forcing of the temperature and salinity. So you get this sort of linear slope, and then it starts to get much colder and also much fresher at the ice base. But if you zoom into the ice base, what's happening is that the finer model has a much different temperature gradient at the boundary. So in our model, we've got these linear approximations of temperature within each cell. So basically, you're looking at what the solution is within the cell. And the way that we've implemented the melt parameter, or I've implemented the melt parameterization, is that it's this particular temperature value at the edge that goes into the melt parameterization. So if you've got changing resolution and those numbers are changing, then you're going to get a different melt. And what's sort of going on is, so there's a geotype. So you have this grids, you've got the grid types, you have this sort of Z layer versus sigma layer. So sigma layer is always generally going to have more resolution in the grounding zone region where you squash the mesh, just by virtue of squashing the mesh. But you've also got to be careful about what the numerical diffusion is, because if you've got you've sort of got diffusion that you're coming from your turbulence model. In our case, it's just very simply just adding on some constant diffusivity in the vertical. And if your grid is also going to, by just having advection and flying around, any numerical method is going to have some amount of numerical diffusion. And I've got a slide just to quickly show that. So this is I was sort of helping to supervise some master's projects, and the key, this is a Rayleigh-Taylor instability. So you have red is a dense fluid and blue is a light fluid, and you're just sort of watching as this thing evolves and the dense fluid is going down, and there's lots of overturning. And what this is, this model actually hasn't got any explicit diffusion in. You can clearly see that over time the interface between the red and the blue has gone down. So when you have these sort of Eulerian grid discretizations, you generally always have some amount of spurious mixing, and that's going to depend on your numerical resolution. So if you come back to this, the point is that when you go from the blue, which is the fine one, to the red, to the black, you keep increasing your amount of spurious mixing, and that's going to change how fast you're mixing temperature and salt at the boundary. And that's kind of captured then in this figure, and it's sort of makes common sense now, but it seemed a bit funny at the time. But if you look at the red line, so this is what the isomet protocol is saying if you use a signal model, so having sort of 30 layers within the cavity, and you can see that as you refine the mesh from, I think this is 18 layers outside the cavity, 36 outside the cavity to 72, you don't really see signs of convergence. It's still like maybe the true melting for this particular set of explicit diffusivity would be down here, but you don't know. And then if you then keep reducing, so if you then reduce the explicit diffusivity by an order of magnitude, that's the blue line. So you can and keep the same grid resolution as this constant red line. You can see that your melt rate has gone down. But if you increase or if you decrease the diffusivity by another order of magnitude, you basically have no change in the melting. So at this point, between the blue and the yellow, you've definitely got completely dominated by spurious grid mixing. So you can say that those results, if you change the resolution, you get a completely different result. And in the black line, the opposite is true. So if you've increased the diffusivity by an order of magnitude, so to 5 times 10 to the minus 4, so still sort of within the realms of things that people would do for simple sort of turbulence, simple turbulence closures, then you can start to see grid convergence. And I guess the key point is that is going to depend on your numerical scheme. So if I'd have plotted MIT, so these are just Firedrake plots. So if I'd have plotted MIT, you might have needed to go to like another order of magnitude diffusivity to get the same kind of convergence. So that was kind of trying to show that I think we understand that isomet plus test case. And that, but it sort of was not particularly satisfactory, especially at the beginning. And sort of what that motivated us, I sort of showed some of those early results without thinking about the numerical diffusivity, but to some people that are more in the Firedrake world and that like analytical solutions. And the key, so what this is showing was a test case that I developed to include melting as part of something called a method of manufactured solution test. So when you're testing a numerical algorithm, the best thing really is to try and see as you make the meshes finer, so you go from that coarse mesh to a finer mesh, you want to see how the error goes down between each mesh. And really what it should do is go down at the order of the order of the discretization you expect. So with our linear elements, we expect to get second order convergence. And you can sort of imagine if you got the melting stuff, trying to find a solution is quite difficult because it's got this sort of complicated physics involved. But what the method of manufacturing solutions does is sort of put everything on its head. And it says that if you choose a solution first, so maybe like some kind of analytical trigonometric type of solution, you can plug it into the strong form of the equation. So here you choose some velocities and some temperatures and salinities, and so you can get out the source terms on the right hand side based on what your chosen form of the solution is. So you plug in these values, and out pops what this forcing term should be on the right hand side. So if you solve the equations with this modified forcing term, then the solution you get should be the solution that you chose. So you can see how your error is going down on different meshes. And I guess the key thing is SimPy is your friend, because you can plug this sort of stuff into a symbolic computing and just come out with these ridiculous expressions for what the things are. So this for instance is that funny Robin boundary condition for the temperature. So you can plug in these temperature and salinities and then come out with what the sort of that gradient should be based on the temperature in the domain. And if you right, so then I think I skipped ahead. Oh, right. So this is just visually just trying to show that you have this very simple. This is the horizontal velocities, but there's like an overturning cell, and you're having sort of the temperature and salinity is kind of like a sinusoidal thing varying with depth. But the point is, if you looked at that on two meshes, you'd say they look the same, but the error is different. And this is looking at a log scale. So you can see that there is a difference in error as you go from the finer mesh to coarse mesh. And I've said that already about the boundary conditions, but the point is the boundary conditions are also defined by the solution. So it's like this quite a nice technique where everything gets pulled together. And if you do, then the line, you can come up with these things showing that all the things are converging at the right rate. This second order convergence. And the nice thing is that because the temperature and the velocity and the salinity are all converging, it means that your melt rates are converging too. So that was quite good. And then right, so I think I'm going to whiz through this very quickly, but so all of that was really model development and model verification stuff. But I wanted to try and apply it to something that looked a little bit like a nice shell cavity. And what this is, this was showing some work from the people I mentioned at the beginning of the talk, from the Thwaites melt project. And this figure is using like a little underwater submarine with a sonar to look at the ice base and look at the bathymetry, and also do some measurements of temperature and salinity using a CPD. And sort of some of the striking features, even though it's been stretched a bit, the striking features are you do see that these crevasses at the ground zone. And there were sort of people that were looking at satellite images, and to varying degrees, people say that trying to understand about these fractures and how they propagate through time generally from the ground zone or areas of in sort of shear margins where the ice is right next to the bathymetry on these nice ice shelves, and trying to understand sort of how these sort of things evolve. And the point is also going back to that original thing from Dutra with the little animation, just trying to understand like how does that affect mixing within cavity. And so Jim Jordan, who was a PhD quite a few years before me, but using fluidity, he had a test where he was looking at fragile ice. So he had a sort of a step in the ice and modeling flow past the ice. And the key point is this depth depending freezing point. So if you have they sort of set up this this test where you have flow past, and then because the freezing point is defined to be for this sort of given initial conditions for temperature, so the freezing point is here, then as when you initially get melting, which goes up, sort of is buoyant, it goes up, and then as soon as the fresh water, or as soon as the meltwater gets above this freezing point, it's super cool. So it starts to freeze and it forms these fragile ice crystals. So you can have a tracer for modeling where the fragile ice is. And that also leads to the density brining ejection. So you're changing the density pattern, which means that you get this sudden sinking. Sorry, so you get sudden sinking coming from the fragile ice. And you might look at that and think that's crazy, which I guess I did. But I met someone at FRISP last year, and they actually had some observations using this little robot under the Cam ice shelf, and they saw these effects on very cold ice shelves. They saw this sort of corkscrew inside a little rift. So whether or not it's that important, it's kind of interesting. And so I was just trying here that we could do a similar thing, and given some good resolution, it's basically the same. And then what sort of the sort of time to spend that work, and sort of where I got to was thinking about the geometry, because in that test case it was all very much you're assuming that the flow is perpendicular to the crevasse. And sort of one of the big things from when you start to go to 3D, really Coriolis is the thing, making sure that the geostrophic balance is mostly what's happening inside the cavity. So I was trying to understand if you have flows that are going in different directions to this crevasse, what happens. So this sort of setup is based on the crevasses from the throat's grounding zone, and the way I was thinking about it, it's like a flume. So you have sort of some turntable with a crevasse on it, and you're moving the crevasse around, and you're driving a flow that's going from right to left. And these are meshes, sort of horizontally unstructured, and more mesh resolution in the crevasse. And this is looking at the velocity fields just underneath the crevasse. So you do see some quite interesting sort of asymmetry. So here, this top left is really just like the Jordan case. And because you've got friction at the ice base, you've got like an Ekman layer that's rotating, so the flow isn't exactly dead on. But you can see that there's much faster flow on the left-hand side than on the right when you have the flow like that. And also, interestingly, when you rotate the crevasse like this, you're allowing the flow to accelerate along the left-hand side of the crevasse. And it's sort of a weird sort of place, because the Rossby number ends up being about a half. So it's sort of like this slightly weird thing where Coriolis might play a bit of a role, but probably is not that important. So it's sort of I think there's a lot more work to try and understand this properly. But you do see some differences. And the key, I think I might have missed the key motivation. So the first bullet point, with the fragile ice, if you have freezing, then you're generating fragile ice, which is going to fill the cavity up. So the whole point is the ocean there is acting to remove the crevasse. And at the same time, when you have melting, so in these cases we're below the depth-dependent freezing point, so we're only really getting melting. But if you have melting, you have the same effect from the isomet plus test case, where you have stable stratification. So you're basically insulating the top of the crevasse from the warm water below. So again, you always expect to have lower melting inside the crevasse than outside. So this is what this figure is trying to show. So this is the melt rates. So melt rates generally follow the velocity, because the melt parameterization depends on the velocity. So you can see that you would get slightly higher melt rates on the left of the crevasse, and generally on the upstream edge. And if you take a profile along y equals through the middle, then you get this pattern, and broadly you still see that you're getting lower melting in the crevasse than outside. So in terms of and this is just zoomed in on the sort of the middle bit, and really what you're showing is that yes, you get these kind of interesting effects that are related to the crevasse limbs. So these sort of grid lines are trying to, if you can imagine in your head where the corners are for the crevasse, that's just showing where they are. So you can see that you're getting different melting based on where you are on the limbs. And the red is like the Jordan cross case. And really the only sort of effect that you're seeing is you have this higher melting on the upstream, And then sort of in the interior, you're getting lower melting really generally than on the outside, and they're sort of slightly modulated by the fact that you've got a flow up on the along the crevasse limbs. And then in the other one is pretty much the same, but in the blue one you do have this slight asymmetry coming from the acceleration of the flow along the left hand side. But really, I think generally that's kind of a second order effect. So you can sort of say that at least from this very sort of first sort of study, it doesn't really show that you're not getting a big change in the melting inside the crevasses just from rotating the geometry. So I think that's kind of where I wanted to stop. So just to summarize, we've developed a new model, and it's a discontinuous Galerkin model for ocean flow under ice cavities. I've tried to be quite careful with the verification by comparing against the well-established model MIT GCM, different resolutions and different test cases, and also developed this MMS test to try and show in a rigorous way that we are solving the equations correctly. And then, so I've done some preliminary adjunct stuff, just looking at the sensitivities, and there's some more stuff, but that was kind of the nicest story. And then with the basal crevasses, we sort of extended some work by Jordan to look at flow rotation, and you do start to see some asymmetry in the melt rates, but generally the melting is still low within the crevasse. And so at the bottom, that was a long list of things that I always wanted to get to. So if anyone's, I mean, I am still very much interested in oceanography, and so yeah, if anyone's interested to have a chat, that'd be good. I think the key thing was really looking at turbines. So all of this stuff was using very simple approximations for vertical mixing, and we had some stuff in the background for doing like 2 equation models, but I didn't really ever get to that. So, and then now, so also very exciting now. So I started this job at ANU. So I'm looking at glacial isostatic adjustment. So it's a similar kind of project, doing model development and trying to get a code that people can use to run glacial isostatic adjustment simulations. And we're using Firedrake for sort of similar reasons, so that it can be an open source piece of software, and so that we can try and make use of the adjunct, maybe as part of understanding the sensitivity fields or inverting things like ice history and unknown viscosity, and in a sort of a 3D setting. So yeah, I think that's where I'm going to finish. So thanks very much. Thank you.
Thanks, Will. If anyone online has any questions, feel free to unmute or pop them in the chat. And if anyone has questions in the room, I can pass around the microphone.
I had a question.
Yep, go ahead.
Thanks for the talk. Really good. I was just interested in the pressure dependence of the melt rate. Does that suggest that perhaps the stress state inside the ice shelf needs to be taken into account if you've got strong winds, or if you've got some other significant stress? Will that affect what's happening?
I'm not too sure. I would think that really it's from this sort of pressure dependence is really coming from like long distances. So it's going from down kilometers down underwater to right to near the surface. So I think I'd be surprised if sort of sea surface tilting of the ice shelf can have an effect. But I mean, there's lots of interesting things about tidal flow under ice shelves, and how sort of tidal interactions with the water column and how that changes the ice. People are quite interested in that, and especially at the grounding zone. So trying to come up with mechanisms for how maybe you get sort of pumping in the grounding zone. Maybe that leads to accelerated mixing. So, but sorry, yeah, I'm not sure off the top of my head if you would get that just from the winds. But it's, yeah, it's an interesting idea.
Sorry, thank you. Thank you for the answer.
Interesting talk, Will. I have a number of questions. Do you model, or do you get an output of the buttressing forces here? We just saw a JRL paper come out.
Oh, okay.
Waves glacier has no buttressing, significant buttressing.
Oh yeah, okay, yeah.
You expect that from your modeling?
So it's really my stuff is assuming that this ice shelf is fixed. So I'm really just thinking that there's some forcing on the top of the domain to the ocean, coming from those melt boundary conditions. So I'm not really worrying about how the ice is flowing, but yeah, I mean it's an interesting thing with those grounding lines and the buttress. That definitely you can come up with some quite interesting calculations to show that. Yeah, it really does depend on the geometry. So it's not always as obvious that if you have an ice shelf, there will be buttress. I think like if you didn't have any geometry, you can just chop ice shelves off and then they disappear. So yeah, it also then it does kind of lead to this stuff that I was thinking about the crevasses, because there were some people that were very worried about these crevasses forming in these shear margins, and like how does that affect the stability of the ice shelves? But if really I think in Thwaites particularly, yeah, they think I think because you've got two different limbs, I think, and on the I think it's on the Thwaites main tongue. Because it's not really being confined, if you remove that, it doesn't really have a big impact. I think it might be completely wrong, but the point was that yeah, you have to be so you have to be careful about whether or not saying that just because you remove the ice shelf, you can have a big effect.
Very nice talk. Could you go back to the sensitivities that you showed to salinity and temperature? I just want to make sure that I understand. So you have opposite sensitivities to the interior and on the edge, like so that is just saying the effect of temperature inside the domain is opposite to having higher temperature at the edge.
Oh, you mean in the at that point there? Or,
Yeah.
okay. Yeah, that's interesting. I think, I mean, the way that I was thinking about it now was more that. So that these things are sort of instantaneous. You've got to be a bit careful how you sort of interpret them. But the idea is what you should do is like an interval over the domain. And if you have some sort of sensitivity pattern or perturbation pattern you're putting on, and then seeing that will affect your melt rates at the final time step. So this is like very much at the final time step. So that's saying if a day before the end of the simulation, you put a temperature field that looked a bit like that, then you would get that increase in the melt rate. And I guess if it's to do with the buoyancy, then maybe what you're doing is somehow changing the flow pattern to get it to look right. But I think the point is you can't say that it's immediately changing the melt rate right then. It's changing the melt rate at the end of the simulation. If you see what I mean. But anyway, it'd be good to talk more about this because there's lots of things that I still don't understand.
The way I see it is just when it's red, it's showing if you increase the temperature there, you're going to get the maximum misfit in your melt. And if you decrease it, then you're going to get the opposite. But then you have 2 points in your domain that are having completely opposite effect. One of them is negative, one of them is positive. So we're just wondering, like, what is the physical meaning of that? But I guess we can discuss it in the office.
Yeah, I'll have to think about it. So yeah, sorry.
Roland has a question online. Roland, do you want to unmute and go ahead?
So William, thanks very much for the talk. From long ago, looking at these sort of studies, I have a couple of questions. First of all, in earlier work with terrain following coordinates, they were identified as being issues with the estimation of the horizontal pressure gradient, and the group here in Hobart, going back to work by John Hunter, found that in fact, for instance, in the Princeton Ocean model, it was possible to generate completely spurious eddies driven by those errors. The second concern generally about sigma coordinate models in an ice shelf situation is whether you simply, if you have the same number of layers throughout, then when you get to the ice shelf front, you have a column of very drastically tilted elements. I don't know if you've noticed any of those effects in your simulations.
Yeah, no, thanks for that question. So I remember reading about a Haney number, and maybe was that related to that sort of stuff, or
So I didn't catch that.
sorry, can you hear me if I speak to the microphone?
I can hear you fine. I just
Oh, great.
spoke too
They're
quickly.
like a Haney number to do with that horizontal pressure gradient error. And
I'm not sure about the,
okay, maybe
the
that's
technical detail. I know that for the Princeton Ocean model, I think this was fixed probably a couple of decades ago by Mellor, because there were things in the code which didn't matter at all if you had an ocean surface that only varied by a few meters. But if you started to realize what a violent difference in the surface it is when you come to a sigma coordinate slanting up the step at the front of an ice shelf, then it started to expose weaknesses in the code. And I was simply wondering, if you think about something that probably would be different between your 3D unstructured simulation and these extruded elements. If you think about it at the ice front, the extruded elements, by the time you slice them up on sigma layers, they have extremely steeply sloping top and bottom surfaces, which in fact become steeper and steeper the tighter you make the resolution. And I'm not sure if there are numerics issues associated with that.
yeah, so we did. So I looked at it a little bit because it was kind of involved in that story going from because I guess the funny thing was that really the whole motivation was to look at grounding zones. So we weren't really ever worried about the ice shelf step, but we did come up with a sort of a hack, if you like, where in the extruded meshes you could have a fixed number of layers inside the cavity and then do a transition over one grid cell to like a different number of layers. And I think what was effective and the way that it was implemented in Firedrake, you had to basically have one sloping interface. That was kind of just a limitation of their extruded mesh thing. And I think in the end, it sort of you have to be a bit careful about how you apply a limiter. So I think probably probably things that really we weren't resolving were getting made disappear by applying a limiter very strongly on that sort of triangular wedge that you get at the ice front. So I think it was sort of saying you pretty much had an instantaneous mixing when you had this very quick change in the number of layers. So I think, and then read the pressure gradient, pressure gradient. I think because our discretization wasn't really, we don't really have to change the mass for when you change the grid. So I sort of always had the feeling that it didn't matter, but it would be good to talk about it a bit more. I think, yeah, because I've seen some stuff with ROMs that we're talking about, not ROMs, with FESOM, I think, they were definitely talking about that, and in the steep slopes that maybe having a problem. But I think, yeah, I guess the point is that we weren't really tied to a grid choice, and obviously the difficulties are always in trying to develop a good grid. But I think like sort of the underlying code is sort of ambivalent about what grid you give it. And that's kind of if that's okay, as a takeaway.
Yeah, thanks. There's one last point, since it's come up in some of the discussion already. I do think that one has to be careful about how you conceptually frame this this pressure depth melting situation. My understanding of this is that what's relevant here is not the pressure dependence so much of the melting point of the ice. It's the importance of realizing that it's the depression of the freezing point of seawater. So the issue is that very cold seawater, when subducted to depth, is capable of delivering far more heat to do far more melting. I think the issues concerning the temperature pressure state of the ice that you're melting is a somewhat less important consideration, particularly here when you're modeling the ocean part. So you're just looking at what sort of heat you can deliver.
Right, okay. Thanks.
All right, we'll leave it there. Thank you everyone for your questions, and thanks Will for your great talk.